Welcome to the kinematics of rigid body motion. Today we are going to discuss the rate of change of a vector. We will begin by letting capital G be a possibly pseudo-vector involved in a mechanical problem. And then the idea is that if we have a reference frame, which we'll call the space frame, attached to the laboratory and another coordinate system attached to a rigid body, then a differential change in the vector G in the space coordinate system can be decomposed in a differential change in the vector with respect to the body set of axes plus the differential change in the body set of axes themselves as they rotate in the laboratory system. Now if we assume that the first term is 0, so that the vector does not undergo a change relative to the body set of axes, then its change in the space set of axes is simply given by the rotation of the body fixed axes. So when the vector G is fixed in the body, the rotation is counterclockwise, and then its differential change in the rotating frame is given by the cross product here, as we have discussed in the previous section, where the vector d capital omega is given by the vector of the axis of rotation multiplied with the differential of the rotation angle. Thus, for an arbitrary vector, generally we have the expression here valid. So for its infinitesimal change in the space set of axes, this is given by the infinitesimal change with respect to the body set of axes plus the rotation of the body set of axes itself. And if we divide this result by the differential of time, we obtain the formula here, where the new vector labeled by omega is the instantaneous angular velocity of the rigid body. But it is not to be understood as a derivative of a vector. Rather, it is defined by saying that multiplying it with a differential of time, we obtain the vector of differential magnitude representing an infinitesimal rotation. So this vector omega lies along the axis of the infinitesimal rotation occurring between the moments t and t plus dt, and this is the instantaneous axis of rotation. In magnitude, omega signifies the instantaneous rate of rotation of the body. Now, if we have the original components of the vector g index I, and we want to express them in terms of the components of the rotated vector, we need to apply the transpose of an orthogonal transformation, right? So the elements here, and given the orthogonality of these of this matrix, this relation is equivalent with the one written here. And if we now differentiate it, we obtain this expression for the differential elements of G. So it's a sum between the differentials of the elements of the rotated vector multiplied with the elements of the transposed matrix plus the differential of these elements multiplying the components of the vector. The space and body sets of axes can always be chosen such that they are instantaneously coincident at a time t. Components are then instantaneously equal between the two systems, but their differentials are not equal since the systems are moving relative to each other. So the components are equal in these circumstances, but differentials are ultimately connected by this formula, which you can see from here, assuming that this relation holds. And then if you look at the differentials of the elements of the transformation matrix, these can only be the elements of the transposed matrix representing an infinitesimal rotation. And as we have seen, this matrix is antisymmetrical, so these transposed elements are simply the ones given here, and then these follow from the definition which we gave to the antisymmetric matrix epsilon in terms of the components of the vector d omega. So this is straightforward from the definition of the matrix in terms of these components in the Levi-Civita tensor. And when the transformation matrix is expressed in this form, then equation 481 in component form becomes immediately equal with what is written here. So this is identical to the ith component of 481, and it is an equation which states how the time derivative transforms between coordinate systems. Furthermore, from the result 482, one sees immediately that the operator for derivatives with respect to time in the laboratory system is equal with the derivative operator with respect to time in the rotating frame plus a cross product involving the instantaneous angular velocity. So when a time derivative of a vector is calculated with respect to a coordinate system, vector components along other sets of axes may be taken only after differentiation. It is convenient to express the instantaneous angular velocity in terms of the Euler angles and their derivatives. The general infinitesimal rotation associated with omega can be resolved as 3 successive infinitesimal rotations having separate instantaneous angular velocities, which are given by the time derivatives of the Euler angles as expressed here. Then the orthogonal transformations B, C, and D of section 4.4 may be used to furnish the components of the resulting vectors along any desired set of axes. To see how this works, we can, for example, attempt to write the instantaneous angular velocity in the body set of axes. So then, for example, the angular velocity corresponding to the rotation with the angle phi is going to be parallel with the original z-axis. So we need to apply the full transformation A of equation 446 in order to obtain the components of this vector in the body set of axes, and its components are simply the ones written here. So these are the elements which will transform a vector along the z-axis into the body set of axes, which you can see immediately by inspecting the matrix of equation 446 and applying it to such a vector. For the angular velocity corresponding to the Euler angle theta, this one is going to be parallel with the line of nodes. So we need, in order to get it into the prime set of axes, we need to apply the last intermediate transformation, so the transformation B, and this will give the components here. And for rotation with the Euler angle psi about the z prime axis, no transformation is necessary, as this is already aligned with the body set of axes. And as such, then the components in the body set of axes, by adding all of these contributions up, are the ones given here. Conversely, we could write these components in the laboratory set of axes, and things proceed somewhat in reverse. So, for example, in this case, as the rotation with the angle phi is parallel to the z-axis, no transformation is necessary in this case, given that the rotation with the angle theta is parallel to the line of nodes. Now we need to apply the transpose of the matrix D, and we get the components here. And since the rotation with the angle psi is parallel with z prime, we get the components here. And once again, if we add them all together, the final result is immediately the one presented here. Furthermore, knowing how to write the angular velocity in different coordinate systems allows us to study the time derivatives of the Euler and Cayley-Klein parameters as follows. For example, if we go back to the expressions of the Euler parameters, we can take E0, its derivative with respect to time, and then we try to eliminate the time derivatives of the Euler angles in favor of components of the instantaneous angular velocity, let's say written in the body set of axes, and we try to recover the expressions of the Euler parameters as well. It's a very simple calculation, but fairly tedious and lengthy, so I'm just giving the results here, which if you're interested, you should check them carefully to make sure that none of the signs are wrong, as this can be a bit tricky. But in principle, the time derivatives of the Euler angle of the Euler parameters should look like this. And of course, knowing them and knowing the relation between the Euler parameters and the Cayley-Klein parameters, we can write the time derivatives of the latter as something which hopefully is correctly given here. Again, it's a very simple calculation, but quite lengthy and tedious, and needs to be checked carefully. As an application, we can consider the case of a sphere of radius a that rolls without slipping on a smooth horizontal plane. And this constraint can be expressed as follows. So as the velocity vector v here represents the velocity of the sphere's contact point with the, let's say, the horizontal plane, and this will be simply given by the cross product between the instantaneous angular velocity of the sphere and this constant vector a, which is in magnitude is equal with the radius of the sphere, and its orientation is parallel with the z-axis. So this would be a vector sticking out of the contact point and being equal with the radius of the sphere and parallel with the laboratory z-axis at all times. And then if we expand the cross product, for example, considering the components of the omega vector in the laboratory frame, we should get the result here. And now if we write the two equations down, considering the components that we have obtained here, these ones, we arrive at the following set of differentials, the two differentials here. And now the same procedure applies like in the case of the disk that rolled without slipping in a plane, which we studied back in the first chapter. So if you apply exactly the same the same approach as we used there, you can see that no integrating factor can be found for either of the above equations that can turn them into exact differentials. So you'll see that if you try to find such a factor, it turns out that it is identically zero. So as such, this particular constraint of a sphere rolling without slipping on a horizontal surface turns out to be non-holonomic. In summary, we have discussed the relation between the time rate of change of a vector when viewed in a space or body set of axes by introducing the instantaneous angular velocity of a rigid body. We have expressed the components of the angular velocity in terms of Euler angles and their derivatives in the space and body set of axes. We have studied a few applications to the time derivatives of other sets of parameters and the motion of a rolling sphere. And in the following, we will discuss the Coriolis effect. That being said, I want to thank you very much for watching. I hope you found the video worth your time, and I will catch you later. Goodbye.